So our imaginary numbers is a difficult concept to understand because how in the world can numbers be imaginary? And it does exist. Imaginary numbers were invented to define the square root of negative numbers. Because what happened many years ago is people were trying to solve problems specifically in physics and chemistry and astronomy, and they couldn't do it because they ended up getting these negative square roots of negative numbers, and they kind of hit a wall, and they're like, well, we can't do this. So that's when they realized that there was these imaginary numbers, and so then it was allowed them to then answer those problems that they were trying to deal with. So the imaginary unit I is defined as the square root of negative 1. So I is the square root of negative 1. So imaginary numbers can be written in the form a plus bi, where a is a real number, so it could be like 3, 5, negative 10, it could be a fraction, it could be decimal. A is just a real number like what you're used to working with, and that b and I are the imaginary unit. Again, I is the square root of negative 1, b is just some number. So you could have like 6i, or you could have negative 7i. So that negative 7 or that 6 would represent your b. So real numbers, this is what you're used to. That is everything you've done before. That's your pi, that's your negative fractions, decimals, repeating, non-repeating, all that kind of good stuff. So then your imaginaries are new ones. Those are your i's. So for example, I, 3i, negative 5i. The square root of any negative number, and I mean any negative number, is imaginary because it would create that I value that we have there. So those are all those other ones. Note the square root of negative 1 squared. Well, this kind of goes back to our last unit. What happens with the square root and the square sign? They cancel each other out. So that's just going to be negative 1. So you can turn an imaginary to be positive again. So if you take I, which is the square root of negative 1, and you square it, you'll get negative 1. So if you square I, it does turn back into a real number. Again, it's something we'll be playing with a lot. So first, let's just practice figuring out where this I comes from. So for our first example, I have the square root of negative 25. So this is kind of like what we were doing before. We would want to separate this into negative 1 and 25, 25 being our perfect square that we are hopefully used to, negative 1 being our imaginary unit. So the square root of 25 turns into a 5. That doesn't change, normal. This square root of negative 1 becomes I. Every single time square root of negative 1 becomes an I. And then we're just used to writing this number first. So this would just become 5i. So for the second one again, we would separate it into the negative 1 and then the 121, because 121 is a perfect square. What is the square root of 121? 11. And then the square root of negative 1 becomes I. So we get 11i from that. So then for number 3, again, I would take out my negative 1 first. And then I would be left with the square root of 7, which is 7 a perfect square? No. Is there a perfect square that goes into it? No. So that's going to actually stay as the square root of 7. That's not going to change. The only thing that's going to change is our square root of negative 1, which turns into I. And just like with your radicals before, anything not in a radical would go in front of it, so that's why I would go in front of your radical, just like a 3 or a 2 would. All right, number 4, this time we got a number in front of our radical sign. We got that 3 there, but still 16 is a perfect square, so I'm going to put my 16 there, my -1 in front of it. So again, the square root of -1 becomes I. It's just got that 3 in front of it. And we would multiply it by the square root of 16, which is 4. So what do we get for our final answer? 12i. Just like any other variable you would use, same rules apply. When you're multiplying, you just multiply those numbers in front of it. So it becomes 12i, just like if you had an x there. So for number 5, 8 is not a perfect square. But there is a perfect square that goes into it. So I'm going to start off with my -1 there. And then what's our perfect square that goes into 8? 4, and then 2. So then again, looking at each piece, that turns into an I. Square root of -1 is my I. I'm going to bring down this negative sign in front of it, so it's actually -I. Bless you. Square root of 4 gives me a 2. The other 2 is not a perfect square, so it's going to stay in the radical. So then anything not in the radical sign we can multiply. And again, it's just like if you were multiplying by an x, it would just become -2i radical 2. If you really can't truly multiply them together, you can just write them together next to each other. All right, 75. So in my first radical, I'm going to put my -1. That takes care of my negative sign underneath there. Second radical, what's our perfect square that goes into 75? 25. And then it's times 3. 25 times 3 gives us that 75. So again, square root of -1 turns into I. So I got a 2i to begin with there. Square root of 25. 5. And then I got my radical 3. So 2 times the 5 gives me 10i radical 3. So when performing operations with square roots that have negative radicals, first rewrite each negative radicand in terms of I, and then you simplify if possible. So again, so that's the very important first step. You always have to first rewrite it in terms of I, and then you can actually go ahead and perform the operation to it. So looking at this first one, we got negative square root of -81 plus the square root of -121. All right. So for the 81, I'm going to first take out that -1. 81 is a perfect square, so I don't need a third radical sign here. What is the square root of 81? 9. Square root of -1 becomes I. And you've got that negative sign in front of it, so it's -9i. Plus, again, take that -1 away from the 121, so now it's a positive 121, which is a perfect square. Square root of 121. So we got plus 11i, so that square root of -1 turns into an I again. So we got -9i plus 11i, which this just follows the same rules as you're adding any kind of variable there. You just add the numbers in front. So -9 plus 11 would give us 2i. It's just like if you had a -9x plus 11x, you'd get 2x. So for for number 8. Again, I'm going to break it apart to -1 and 9, because 9 is a perfect square, so I don't need a third one. Square root of 9, 3. That square root of -1 becomes I, so I got 2I times 3. So that becomes 6I. For the other one, 49 is a perfect square. So I'm just going to take away the -1. So then this becomes 5I times 7. So we got a -35I. So it's 6I minus 35I. -29I. Now for number 9, those aren't perfect squares. 48 is not a perfect square. 12 is not a perfect square. So we're going to have to do the 3 radical signs. -1 is my first one to get rid of that negative sign. And then what's the perfect square that goes into 48? There's a couple of them. Yep, 16 would be our largest one. 16 and 3. So in the square root of 16 is 4. That square root of -1 becomes I, so I got 4I outside of my radical 3. So 4I radical 3. Same thing with the 12. 12 is not a perfect square, so I need to set up my 3 radical signs. First one being the -1. And what's our largest perfect square that goes into 12? 4. Square root of 4 becomes 2. We get an I from that square root of -1, and then our 3, so 2I radical 3. So now since our numbers underneath here are the same, this goes back to our last unit, we can actually subtract these. So 4I minus 2I gives us 2I radical 3. And for the 18, we start with the 3 radicals, because 18 is not a perfect square. What is our perfect square that goes into it, though? 9, 2. Square root of 9 is 3. So I got 3I times 3 outside of my radical, because I already had some stuff there. So I multiply those 3's. I get 9I radical 2. So then for our 72, it's going to be the same thing. 72 is not a perfect square. So we're going to take out that -1. 36, good. That's our largest perfect. So the square root of 36 gives us a 6. Again, that square root of -1 gives us I. They both are a radical 2, so we can actually add those together. So 9I plus 6I, 15I radical 2. All right, we got 2 more. So for 11, is there a perfect square that goes into 10? No, so I don't actually need that last one there. Just going to be -1 and 10, because there is no perfect that goes into it. So that gives me 5I radical 10. about 52? Is there a perfect square that goes into 52? 4. 4 and 13. That becomes 2I radical 13. Square root of 4 gives us 2. Square root of negative 1 gives us I. And we got our radical 13. So are these the same numbers underneath the radical sign? No. So we can't combine them. That's your final answer there. So I'm looking at our last one. What's our perfect square that goes into 27? 9. And 3. Square root of 9 is a 3. But then times that 4I, that was already out in front, gives us 12I radical 3. What's our perfect square that goes into 50? 25 and 2. So the square root of 25 would give us 5. Then we get the I from the square root of the negative 1. And again, for these ones, they don't have the same numbers underneath the radical sign. So that ends up being your final answer there, 12I radical 3 plus 5I radical 2.